Hello, everybody. So we are going to now talk about, in the last video, we talked about the fundamental theorem of calculus part 1, and now we're going to talk about part 2. And just to be clear, the names part 1 and part 2 aren't universal. Some textbooks might approach this the other direction, starting with what we called part 2 and calling that part 1, and vice versa. I guess that is the whole thing. Some people just present it as one theory, and that's fine. We're just splitting it up just to make more digestible chunks. But if you're going to look for more information, just be aware of that this isn't the fundamental theorem of calculus is typically called the fundamental theorem of calculus, but the part 1 and part 2 aren't necessarily presented that way in all instances. So I want to start talking about, I've got part 1, what we called part 1 written here from last time. We're going to use that in a little bit. Remember what this was that if we define a function g, g of x, as the integral over another function from a up to x, right? It's this interesting function that you plug in a value, it spits out the area between a and that value of x between the x-axis and the graph of f. Right? We said, well, when you do that, when you take the derivative of g, you simply get f, the function, the integrand, that function in the integral. So let's just kind of put that in the background for now. We're going to use it a little later. And let's come back to something we've talked a little bit about before, the idea of position and velocity. You might remember from a differential calculus class that if you have a function x of t that represents the position of some particle at time t, then you take its derivative, you get the change in position over change in time, which is a velocity. And so the derivative of position is velocity. So let's say what I have here is a graph of the velocity function, and I want to take the integral from a to b of the velocity function, right? That area that I've shaded in green here represents whatever number this integral here would compute to, okay? So let's think about what this means. So we talked about this a little bit in a previous video, but let's go back to thinking about our rectangles, right? If I remember how we do an integral. At its core, even when we learn the shortcuts, and we're about to learn our first big shortcut today. I guess one shortcut we have is if it's a geometric shape we know, we can just use the geometry rules we already have. But otherwise, we're left with trying to take these limits of these Riemann sums. And when we do that, we create these approximating rectangles, right? So here's an approximating rectangle that happens to be using the left endpoint. Doesn't really matter for this. And remember what the area of this rectangle is. If we called this, in this case, it's going to be delta t. And on this side, it's going to be v of t, let's just say t sub I, right? And this area is v of t sub I delta t. Let's call it a sub I, that approximating rectangle. Well, let's just think about units for a minute. The units of this velocity is going to be in, let's say, meters per second. It could be miles per hour, inches per year, right? If you're measuring the velocity of maybe continental drift or something like that. But meters per second, and then time is going to be in my example, seconds. I'm just going to put it over 1 for clarity. Meters per second times seconds gives me meters, right? In other words, we've computed the distance it traveled in this time interval, or at least the approximate distance. We pretended it traveled at the velocity it was traveling at the left edge, at the first edge of this interval. And if it traveled at this speed the whole time, right, if the speed there was 10 meters per second and maybe delta t is 1 second, we would say, oh, if we traveled 10 meters per second for 1 second, we will have traveled 10 meters. Of course, it's an approximation. We see that we're actually slowing down. But that whole time we're taking the limit, that holds. And so this approximation and in the limit is giving us distance, right? So this area, right, this area that we are finding here should give us the distance traveled well, let me be more careful, the total displacement during the interval from A to B. Okay, and I'll mention why I had to be careful there in just a moment. Okay, so the total displacement, right, is just the difference between where you started and where you finished. In other words, if I take my position at the end and subtract my position at the beginning, that should give me the total displacement over that interval. Okay, this is a pretty big deal. Notice what we have here. I want to integrate over, find the area of this, fairly complicated shape I've drawn here of this function. In order to find it, I simply evaluate the position function at the endpoints. And let's remember, the relationship between velocity and position is that velocity is the derivative of position. Another way to say that is position is an antiderivative never remember if that has a hyphen in it. Position is an antiderivative of velocity, right? That just means that it's like the opposite direction of that sentence, right? If I say the derivative of x is v, then the antiderivative of v is x, which is going in the other direction, okay? This turns out to be, I haven't proved anything yet, but this turns out to be the other part of the fundamental theorem of calculus, that to calculate these areas, we can skip doing all that Riemann sum, taking limits, and instead we can go hunting for antiderivatives. And that's going to be a large part of what we do, okay? So we're gonna formalize this statement in just a minute. I wanna go back to a thought I had just a second ago about total displacement versus, let's just actually move off to the side here, versus distance traveled. Let's look at a similar situation, except I want to change just a couple of small things. So let me do another graph of another velocity integral situation. With one big change, I'm going to take my graph of v, right? Let's just draw it again and make it go negative at some point, okay? And so let's say now we were looking for the integral of v, so this is still a graph of v of t. We still have that x of t is position, x prime of t is velocity, and our area is going to be, let's make this bigger, right? We're going to be looking for, see, I'm learning new tools in each video. So I've got this nice little, this is more or less the area we're looking for, right? Still learning. Okay, so that's the area we're looking for. However, notice that now some of the area is negative. What does that mean about velocity? It means sometimes it's moving in the negative direction, right? So if we have a particle, let's say I have a particle, located on some kind of vertical bar. Maybe it's inside some kind of hollow tube and it moves up and down as the pressure changes. Let's draw ourselves a little picture. So maybe it's part of a barometer or something like that. And I've got a little particle in here that will move up and down depending on how the pressure changes outside, right? So we might say positive is up, negative is down. So what this graph is telling me is that I started with an upward velocity, right? I was moving in the up direction for a while. Then I moved down, or the particle moved down for a little bit, and then it moved back up a little more, right? So the first area, let's call this, just call it area alpha, beta, gamma. In the alpha area, we're moving positive, and it looks like by a fairly large amount. We move a little bit in the negative direction, and we move a bit more in the positive direction, right? So the total distance traveled, well, if let's put some numbers on here. Let's pretend we knew the area here was 5 units positive, 2 units backwards, and 4 units forward. Then I've traveled, my particle has moved a total distance of 5 units, 2 units, 4 units, so 11 units, right? It doesn't matter if it's backwards or forward. I'm just saying, how much has this thing moved? And I'm counting in both directions. On the other hand, the total displacement is just between where it started and where it finished, right? So in this case, it started out, and we don't know what number it started out at. I've drawn my picture, it's somewhere in the middle, right? Wherever it started out at, it moved 5 forward, 2 back, 4 more forward for a total of 7, right? So its total displacement, the difference between where it finished and where it started, is only 7. That takes into account the negative nature of the velocity here, right? And so when we take an integral, if I take the integral a to b v of t dt, we get the total displacement, right? And this is often what we want. If all I care about is where did my particle end up, or how far away from its starting point did it land, that's exactly what we want. On the other hand, maybe sometimes you do want to know how far it's traveled. Maybe the thing we're using in our barometer has a limited lifespan, and every time it moves, it accumulates some damage, and we might want to keep track of how far it moves regardless of which direction. We have a simple way to do this, and we're going to talk a lot more about this in another video, but I'll just mention it here. We can simply take the absolute value, right? And this would give us, so I should not use abbreviations, total displacement, and this would give us the total distance traveled, right? Because what does it do to the function? It just changes the function from negative to positive when it's, let's use, where the function was negative here, it leaves it alone where it was positive, and it changes it to a positive where it was negative, so it adds up all of that that negative part. But we're going to talk a lot more about that later. So let's leave that as it is for now, and let's carry on with talking about the fundamental theorem of calculus, part 2. So let's state it. I gave an example here where it's velocity and position. This is a great example in calculus. It works pretty well intuitively, but this is going to hold true for all functions. And let's state it now with clarity and generality. We can say if, let's see, a function f is continuous on the interval ab, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is an antiderivative of f, right? Meaning, if I take the derivative of capital F, I get little f. Okay, and that's it. It gives us this wonderful way to compute these derivatives by finding antiderivatives, which, like I said, is going to be a big focus for a lot of the videos that are coming in the next few days, or probably weeks, really. Okay, let's give a sketch of the proof of this. Okay, and we're going to use the first part of the fundamental theorem of calculus to prove this. Okay, so let's let g of x equal the integral from a to x of f of t dt, and I should put where f is continuous on AB and x is going to be between a and b. So we're just defining a function as we did in the first part of the fundamental theorem. Then we can say by the fundamental theorem of calculus part 1, g prime of x equals f of x. Okay. Let's see, let's have let f, capital F, be an antiderivative of lowercase f, which means f prime equals f. Well, notice that means that f prime is equal to g prime, because both of them are equal to f, okay? Yeah, let's make a quick comment on that. So you might wonder then, are they the same function, f and g? Not necessarily. Two functions can be, well, I guess we're about to say it anyways. Two functions can have the same derivative, but not be the same function. This is a result that's usually taught in Calc 1 and differential calculus. Let's suppose I have two functions. Let's see if this works. Okay, I don't know how to do that yet. So let's say I have two functions and I'm trying to draw them to look exactly the same, right? Now let's use the names we have here. Maybe this one is capital F and this one is capital G. They're not the same function, right? They're not the same function, but they would have the same derivative. If they have the same shape, remember all that connection between derivatives and shapes of functions. Well, they have the same shape, they're going to have the same derivative. This can be proved more rigorously. It's done in most calculus textbooks, and you should have seen it at some point in an earlier calculus class. Happy to do it. If somebody has questions at some point, you can request a video on that. But notice this means something else. If two functions have the same derivative, we can't say they're the same function, but what is true is that the difference between them is just a constant. If this capital C is a constant, just some real number, that has to be true if their derivatives are the same, okay? So we're gonna actually use this fact. So f is equal to the function g plus the constant c. So I'll say where c, and I'm gonna use a symbol here, this is a little symbol to mean, is in the set or is a member of the set. And then this symbol just means of real numbers. So this just says where C is in the set of real numbers. It's some real number, okay? All right, what can we do with all this? Well, let's look at f of b minus f of a. So remember, right, that's what we're saying this integral is equal to. Right, the integral from a to b of little f of x dx should be equal to capital F of b minus capital F of a. So let's see what happens to capital F of b minus capital F of a. Well, let's use this fact that the difference between f and g is just a constant. So I can substitute in for f of b, g of b plus whatever the constant is, minus g of a plus whatever the constant is, which gives me g of b plus c minus g of a minus c, which gives me g of b minus g of a. Now, let's look back. Sorry, I lost track of where I am. Let's look at g. What is g of a? G of a is the integral, so I'm looking back at this definition of g that we started with. G of A is the integral from A to A of f of t dt. From our properties of definite integrals, if there is no actual interval, if it's a single line, it has no area, and that area is 0. So G of A is simply 0, so this whole thing is G of B. Right? So f of B minus f of A is equal to G of B. What is G of B? Go back to the definition. G of B, according to the definition, G of X is equal to the integral from A to X, but we've put in a value for X. We've put in B, f of t dt, and this is all on the left-hand side, f of B minus f of A equals the integral from A to B, f of t dt. Okay? And that's it. That is the proof I'm going to give for this. Okay, this is a pretty big deal, right? In combination with the first and second part of the fundamental theorem of calculus. So let's move this up here. Let me get this. Whoops. Let's see. There it is. Let me move this up on the side here. We now have these two theorems that I can together just call the fundamental theorem of calculus. Right? The first one, we have this continuous function f, continuous on A to B. Then the first one, it relates the derivative of g to the function f in the integrand. The second one says when we integrate, we find an antiderivative to do this integration, right? I've also put in this alternate notation down here. Maybe I'll make this a little bigger. Right. Put in some alternate notation here of what these two things say together. And what we're essentially seeing here, without being totally precise, is that integration and differentiation are inverses to each other. It's not precisely true. There's a couple little details that we will work out to see how they're not quite inverses of each other, but we can see this very clear back and forth relationship. When we take the derivative of g in the first part, we lose our integral, right? And when we take the integral here, we're going backwards from the derivative. Or when we look at this alternate notation here, the integral of f prime of x dx is f of b minus f of a, okay? So they're in some sense reverse processes. This is a pretty surprising result, right? On the one hand, we studied slopes of tangent lines, and then on the other hand, we're studying area, and somehow those two things are connected, right? They don't feel, at least to me, intuitively connected, but it turns out that they are really, kind of two sides of the same problem, which is an idea we will explore quite often in this series of videos. All right, let's do one more thing. Let's use this thing so we really see what exactly it is I'm trying to get at with this. What exactly do all these things say? And this, I hope, makes clear the meaning of this. So I'm just putting in a line of separation. That's not an axis. So in one of our other videos, we computed the integral from -1 to 5 of 1 plus 3x dx, and we got the result of 42, and we did this using the limit of sums, right? Well, now let's use it, let's compute this. We also, I think, looked at, you could compute it, oh yeah, we did do it with areas of triangles, because this is just a line, and the area between the line and the x-axis gave us a couple of triangles, one positive, one negative. That's in a video or two back. Let's use the fundamental theorem of calculus to solve this now. So 1 plus 3x is certainly a continuous function, so we satisfy the conditions that we need for f to be continuous. And so in order to solve this, in order to compute this integral, we simply need to take f of 5 minus f of -1. That's super easy to write down. The tricky part is where f is an antiderivative of 1 plus 3x. In other words, I need an f of x such that f prime of x is equal to 1 plus 3x. Okay. Now, we are going to do some work. Again, I keep saying in later videos, but we'll get there. How do we find these antiderivatives? Right now, we're going to develop some rules, but right now, all we're going to do is kind of guess and check our way there. So let's look at 1 plus 3x. We know when we think about derivatives, right, if I take the derivative of two functions, let's just call them a of x plus b of x, I get a prime of x plus b prime of x, right? So I'm looking for the antiderivative of two functions here, right? So I can think of each of these separately to get these a and b. So I'm going to start by thinking, what function has an antiderivative of 1? And there's no big trick here, I'm just remembering. And it occurs to me that the function x has a derivative of 1. Okay. I'm also remembering from derivatives that constants are kind of not a big deal. When you have a derivative of a constant with a constant, the constant just moves to the front. So I'm going to focus on the x part. What kind of functions have derivatives where you have a power of 1, an x with a power of 1 on it? Well, remember with derivatives, when you take a derivative of a power of x, it goes down by 1. So if I had an x squared right here, when I take the derivative, I will get an x. The problem is I'll get 2x. Okay? But I can fix that simply enough. I don't want that 2 there. I do want a 3. So what I'm going to do is put a constant in front of it. It's going to have a 2 in the denominator and a 3 in the numerator. If I take the derivative here, the derivative of x is 1. The derivatives of 3/2 x squared is 3x. Right? I found an antiderivative. And notice in the statement up here, any antiderivative of f. There might be another one, and we'll talk more about how there can be in just a moment when we finish this problem. But I don't need to find any particular one. I found the one that I care about, right? Or I found a1, and that's all I care about, that it is an antiderivative, right? Just to clarify, f prime of x is equal to 1 plus, take down the 2, multiply it by 3/2, get 3, and I'm left with an x. So that tells me the f I need to use, f of 5. So now I'm just plugging in 5 to this capital F function that we found. That's going to be 5 plus 3/2 times 5 squared minus -1 plus 3/2 -1 squared. What are we going to get? We'll have 5 plus, let's see, 3 times 25 gives me 75/2. I'll get a +1. The -1 squared is a +1, and then I distribute the negative to the 3/2. I get -3/2. Let's just add together the whole numbers. I get a 6. 75 minus 3 gives me 72/2 x, which is 6 plus 36, which is 42, which is exactly what we got when we did it, doing it by Riemann sums and taking a limit, when we did it by looking at the graph and taking using triangles and using geometry to compute that area. Okay. All right. And I believe even the triangle option, this one seems a bit easier, right? The triangle option required a little, like I did a lot of the work for you. I found the intercept, all these kinds of things that might have taken some more time. Once you're practiced at finding antiderivatives, and it's going to turn out to not be all that difficult for at least functions like this problem will become a no-brainer. It's pretty simple to go through. Notice I said with practice, right? It's certainly not an easy problem at the moment. It's going to take some time to get there. All right, one last thing. Let's dig into this idea of an antiderivative. I found capital F of x here is an antiderivative of 1 plus 3x, right? What if I'd added something like 17 to it? This is still an antiderivative of f, because if I take the derivative, right, I don't have to change anything about the f prime here. The constant just disappeared anyways. So I have a different function, but that area hasn't changed. Let's see what's going on. Let's compute this -1, 5 to 5, 1 plus 3x, the integral from -1 to 5, 1 plus 3x dx, but using this different f that I've just come up with up here. Right? It's still going to be f of 5 minus f of -1. And we're going to get 5 plus 3/2, 25 plus 17 minus -1 plus 3/2 times -1 squared, and we'll get a plus 17. Now notice what happens. I get 5 plus 75/2 plus 17 plus 1 minus 3/2 minus 17, right? This line here is exactly the same as this line here, except for this plus 17 and minus 17, and those are going to disappear, right? These two things cancel each other out, and now we have exactly the same computation. We get our 42. Okay, so the point is, those constants, while they aren't wrong, only serve to confuse things when we're computing a definite integral. We will learn in the near future that sometimes those constants have meaning that we're going to have to care about. But when we compute a definite integral, we do not need to worry about what constants are here, because they disappear in the computation. Okay. We'll do some more videos with some more examples of using this, figuring out antiderivatives, all that sort of stuff. More to come. All right. Thanks, everybody. I will see you next time.